The question here is, could you summarize the individual loadings that are generally combined? At the outset, let's state the principle that we use in combining stresses produced by different kinds of loading. The stresses induced by different load types, such as the axial load N, bending moment M, shear force V, etc., can be combined provided that the material behavior is linear and elastic. And this is what is called the principle of superposition. So let's go ahead and list some examples of commonly encountered individual loading types. Here's one, a one-dimensional rod subjected to a tensile axial force N. Let's assume that the axial force N is acting at the centroid of the section, so it doesn't produce any bending moment about the z-axis or y-axis or anything like that. We typically say, oh well, an axial load produces an axial stress, right? But what kind of stress is that? Now when we try to combine loadings, we want to be very precise about the planes on which they act, whether they are normal stresses or shear stresses, and the directions in which they act. So I'm going to take a general point like point A and draw a little differential element around that point. The faces of this differential element are perpendicular to the x, y, z axis. X-axis is the axis of the rod, y-axis goes in that direction, and the z-axis goes in this direction, perpendicular to the paper. So this is exactly the stress produced by the axial force N. It is a normal stress acting on the x-plane in the x direction. It is also a tensile stress. The magnitude of the stress is calculated by this simple equation, right? Sigma xx equals N over A. The force divided by the cross-sectional area of the section. There are no other components of the stress acting on this differential element. Our second example here is a rod subjected to PO bending, like shown in this picture here. And this too produces a normal stress, like shown in this picture. At point A, this is going to be a compressive stress, so these arrows reflect that. The magnitude of the stress is given by this bending formula, sigma xx equals mz times y over iz. And iz here is the second moment of inertia about the centroidal axis z, and the y, of course, is measured from the centroid going vertically up, right? In these two examples, as you notice that I have used a rectangular one-dimensional beam as opposed to a circular rod. I did this just to avoid confusions about the coordinate axes. But these ideas are equally applicable to beams with a circular cross-section or a trapezoidal cross-section, provided the cross-section is symmetric about the y-axis. Our third example here is a beam with a transverse shear Vy. This shear force produces a shear stress as marked in this picture. I call this tau xy because the shear stress acting in the x-plane in the y direction. And of course, there is a complementary shear stress acting on this plane. Tau xy is given by this general equation, Vy times q over Iz times t. Iz here is the second moment of inertia about the z-axis, but I'm assuming that you guys remember the definitions of q and t. So here's my fourth example, a circular shaft subjected to a torque T. And here the x-axis is taken to be along the axis of the shaft. R is the radial direction, theta is the hoop direction. Here's a little differential element drawn with respect to this cylindrical coordinate system. The torque produces a single shear stress component like shown in this picture. And I have indicated that by a little arrow over here as well. So the direction of this is perpendicular to the radius r. I call this tau x theta because it's acting in the x-plane in the theta direction, in the hoop direction. The magnitude is given by this torsion formula, tau x theta equal t rho over j. T is the torque, rho is the radius, j is the polar moment of inertia. Here's my final example, a pressurized thin-walled cylindrical tank. Using the same cylindrical coordinate system as defined here for the torque problem, these are the stresses acting on this little differential element defined in the cylindrical coordinate system. There is a normal stress on the x-plane. There is a normal stress on the hoop plane, right? And this is given by this formula right here. This is given by this formula. So it turns out sigma theta is twice as much as sigma x. So sigma x is PR over 2T, where P is the internal pressure, R is the radius, and T is the wall thickness. So let's go over one or two examples of combined loading problems. Here is one. We have a simply supported beam subjected to an axial force over here and transverse loading like shown over here. We have a distributed load over here and a point load acting at this point. If I were to section the beam at point A and look at the internal forces, I'm going to see this. I'm going to see a shear force V, a bending moment M, and the axial force N, right? Supposing say we have a rectangular cross section for the beam and I'm interested in looking at the combined stresses at point A. This is what we have. The shear force V produces the shear stress tau xy, and whose directions are shown over here. Both the bending moment M and the axial force N are going to produce a normal stress on this x-plane. So the normal stress here is going to consist of two parts, sigma xxn, the part that comes from the axial force N, and sigma xxm, the part that comes from the bending moment. And of course they have to be combined with proper signs, and we would know the signs until we find the internal forces on that section, right? So we have to solve the actual problem, find the internal forces, and then we will know the signs for each of these two components. That's it. So these are the combined stresses at point A for this problem. Here's another example. I took the earlier example where we had a cylindrical shaft subjected to a torque T and added an additional axial force N. Here are the combined stresses at point A. All you have to do is to mark the shear stresses produced by the torque and then add the normal stress that comes from the axial force N. Sigma xx is the normal stress on this x-plane in the x direction. And it is a tensile stress because this force is a tensile force.